Hello everyone, welcome to the second part of DPO paper explanation and implementation. So if you haven't seen the part 1 video where I've explained about the paper in detail, including the advantages of DPO where it is very computationally efficient and also it might serve in future as an alternative for RLHF based approaches because while experimentations it has shown the potential that it can perform as much as RLF or even better than RLHF based algorithms. Okay, including the one which was used in ChatGPT, which was PPO. Okay, so that is DPO. Okay, so here in this video, in the second part, we are going to implement this DPO on a model. Okay, and we'll see how it will perform. So for this, we have took tabby ml Santa Coda 1 billion as usual. Okay, and I hope you guys have seen this file from our previous video itself, where I gave a short tease of what in this video will be getting as a final output. Okay, a model when asked a question about should should you buy a case to protect your cell phone in a general way, it was replying something like in Java code, right? But it doesn't make any sense to reply in this fashion for this question. But here, if you see, when I fine tuned it in an SFT stage, followed by applying DPO, we were able to get some results which made some sense. Like it was saying, I would like to help you to protect your phone or something like that. Okay. And this result is not something I would say it's great. But once we see the DPO file, right, you will understand this itself is making great sense that I'm saying it is very good. Okay. So I'll say which are all some parameters you can play with. Okay, because here if you see we are using this Santa Coda 1 billion, but from TabbyML this guy itself has, or this organization, I don't know if it is an organization or an individual, they have created some good small models actually, like we're having Star Coda 1 billion, we are having Cogent 2 billion, there is J350M, so you can try with some models. Okay, for now I'm just keeping it to TabbyML Santa Coda 1 billion. Okay, so let's start with SFT, because even in our previous video we saw, right, where while explaining the process of DPO, we saw that first we need an SFT model. Okay, so that was the base even in RLHF, right? We were trying to skip or bypass the reward modeling step, but others remain the same. So still you need to do an SFT fine tuning. So sorry, SFT, because it is already called a supervised fine tuning, so it doesn't make any sense to call it as SFT fine tuning. So we need to create a SFT model, followed by which we can apply DPO on top of it and possibly make some good results. Okay, so without uh, any further delay, we'll move on to the implementation. Okay, so guys, I'm just making a walkthrough because if you see, we are having two long files along with an inference. Okay, and possibly I might even show you some things from the source code, how they would have gone about it. So it will take some time if we code it in live. But if you're not comfortable with me going in this fashion where I make a code walkthrough, let me know in some way. Like you can connect with me through my social links, which is given in the description, or else even you can join our Telegram group where I'm open for some healthy discussions. Okay, and maybe even if you want, you can just let me know in the comment section. So, yep. Now let's start with installing the dependencies. Okay, so for the first dependency would be transformers library, followed by TRL. Okay, TRL is a recent library which is being released by Hugging Face, which is transformer reinforcement learning. But for the guys who have been seeing our videos, I don't think this any of these libraries should be new, because we have used the similar setup for fine tuning Llama. So guys, if you haven't seen how to fine tune Llama 2 by using the similar setup, but the Llama 2 7 billion model was even fine tuned in Colab itself. So if you are interested in fine tuning Llama 2 on your own, just check our video playlist, where there is a playlist name called LLMs related, where I'll be posting videos mostly on LLMs. There are two videos right now, which is one on fine tuning Llama 2, and other is on deploying a chatbot on your own. Okay, not chatbot, any LLM on your own. So if you are interested, just check it out. So coming back, we are having PEF library, okay, from which we'll be using LoRA, and then accelerate. We are having datasets library just to import dataset from the hub, and then bits and bytes to load it in 4 or 8 bit, because we are doing QLoRA, okay, not just LoRA. We are doing QLoRA, which is LoRA on quantized weights. So as usual, guys, we need to do notebook login, okay? And I hope you guys know how to create the token. So we have seen that in a lot of our videos. Now let's see the inputs, okay? So thanks to, before moving into the implementation, thanks to Hugging Face, okay? From their implementation, we have done this, okay? So thanks to them. Hopefully this will make us being enabled to train a lot of LLMs. Okay, that too, which will be generating according to our preference. That is the key point here, right? So here we have data classes, typing, torch, datasets. Then these are all some conventional ones, right? But here, if you see, we are having auto PEFT model for causal LLM. We have seen auto model for causal LLM. Here, what is AutoPEFT model for a causal LLM is that it will try to load the PEFT model directly. Okay. Previously, we used to load the causal LLM model, and then we will be combining it with the LoRA module by using get PEFT model, right? But here, if we have the config file, we'll directly load it. Okay. So we have our LoRa config, we are having TQDM, and then auto model for causal LLM. These are all some conventional ones. Okay. So, and then we are having this are two new things. So SFT Trainer for supervised fine tuning and constant length dataset to maintain a similar length in the whole dataset. Okay, so these are some helper functions we'll see once we go through this. Okay, so first we are having a function called def create datasets. Okay, this will take tokenizer as input. For dataset, we are going to use this dataset, okay, Dahoas full-hh-rlhf. And I think there are, I haven't said about the full name for HH-RLHF till now in any of our videos, though we have seen about this in one or two. HH means harmless and helpful, okay. RLHF is reinforcement learning with human feedback. Here we'll hold out this train set for or DPO, and test set we'll use it for SFT. But I would suggest the opposite. If you're having time, train it on train your SFT on the train subset rather, and then train your DPO model on this test subset. Okay, and don't forget to hold out some part of it for evaluation. So here, if you see, we are taking the split test, okay, and use auth token is equal to true. Just make it enabled, okay. Then usually we'll convert into pandas data frame, but here we can also directly do train test split, where you can provide your test size, and for now I've set seed is equal to none, okay. So from this we are getting the train data and valid data, okay. So once that is done, next we'll be having our train dataset and valid dataset becoming as constant in the dataset. Okay, before that, there is this function called cache token ratio. Okay, so let's go into that. In cache token ratio, what it will happen is the main idea of the function is to find what is the average number of characters per token, okay, in the dataset. For now here 400 samples has been taken as the range. Okay, so in 400 samples, each sample is tokenized, and in each token how many characters is there, that is what is going to be returned from this cache token ratio. Okay, so now that is done. Followed by this, we are having train dataset and valid dataset. Okay, I hope now this makes some sense. Okay, for this, we are going to use constant length dataset. So for constant length dataset, what it will happen is I'm just going to show you that here. Okay, let's see here if it is there. Constant length dataset. Utils maybe. In utils, it should be there. Wrong spelling. So here you can see, right, there is a class called constant length dataset where it will return a dataset which will have constant length of chunk of tokens. Okay, so what it means is that uh, whatever length we give, right, it will try to provide it in a constant length, like it won't be varying. Okay, so that is what constant length dataset class does. And don't worry, I'll make a playlist on TRL very soon, TRL library. But if it is the most intriguing one for you guys, just let me know. I'll make sure that that playlist comes out soon. Okay, here if you see, for this constant length dataset, we are providing tokenizer, train data, and formatting function is provided as prepare sample text. So what we do in this formatting, so here what you can do is actually this won't be needed. Okay, so here if you see, we are having human and assistant kind of conversation, right? Human assistant. Okay, so you guys can just leave it like this. It will be finally like, assistant will be there, and then, yep, you can just maybe use this. Okay, what will happen is we are having a column called prompt and response. So it will just try to combine it like this, right? Human and assistant, like, after this in a separate line, this will come down. Okay, so that is what will happen. Like, we are just combining these two into a single text value. Okay, so given an example, we'll get prompt and response, and we'll just combine it. Okay, so that's what is happening here, and that will be our formatting function. And we are having a sequence length of 256, and cache per token we have calculated, right, by providing the train data and tokenizer. It will be provided here. So similarly, we are creating the valid data set. So now if you see, we have seen about this cache token ratio, and we have seen about prepare sample text and create datasets function. Now it is time to prepare our model. Okay, so first we are creating a bits and bytes config so that we can load the model in 4-bit. Okay, so load in 4-bit is equal to true. So this is from bits and bytes package. So there is one person called Tim Detmus. He does some amazing work. So if you want, just follow him in Twitter or even in LinkedIn. Okay, so he's the one who is managing this library. Okay, so load in 4-bit is equal to true. So next we have BNB 4-bit quant type. So it will be NF4, normal float 4 precision. Okay, and then bits and bytes 4-bit compute data, which will be top star 416. These are all some conventional ones now, right now, right? We have seen a lot of projects by using this kind of configuration. For now, we are taking our base model as tabml Santa Clara 1 billion. Okay, we have seen that, and we are parsing this quantization config so that we can quantize the model in 4-bit. So applying the device map to be 0 so that every layer will be mapped to the CUDA device 0. Okay, and then trust remote code equal to true. This is something you can just do it at any time. Okay, because there will be sometimes that it will be needing some code. Okay, so which is from their source file, which is not even available in Hugging Face. To enable those changes, always it is good to have trust remote code is equal to true, and then use auth token is equal to true. Okay, now since we are training, we are making the catch as false. Now we are done with creating a model in 4-bit. Now next step is to add LoRA modules, right? So we'll see how to do that. So we are having LoRa rank is equal to 8, LoRa alpha is equal to 16. We are providing dropout as 0.05. Target modules. How to see this target modules? This is something you need to know. Okay. So once you where was that? Yes, here is your base model, right? So usually we calculate this LoRa, we add this LoRa modules only for attention modules, okay? But here in our previous video, if you see, we would have done it for query value, and in some other videos like Llama will be having QProj and VProj. Okay, the module name will differ. That is very important. Okay, so to find which module you need to do, what you can do is you can just print your base model, and then it will show like attention somewhere, it will be written. There you can find which is your attention module, and then you can just add it. Okay, so maybe even I'll try to do that at least. Okay, if not for the whole code, at least I'll try to show you how to find your attention module. Okay. And so guys, also if you don't know how LoRa works, okay, and if you are interested to know like how to set these parameters, what these parameters does, we have made a detailed video on our channel, okay, where I've explained about LoRa, its working, as well as its implementation examples. Okay, so it is in the similar playlist, research playlist itself. So check it out. Yep, I guess now we should pass the token. I guess that shell would have been run. Let's pass this token. Okay, now what I'm going to do is I'll have these alone in a separate set. But we'll need the input, right, for these auto model for causal LM and bits and bytes. Okay, I think it's better to import this one. This won't be needed actually. So not run these. From PEF library, we'll be needing LoRa config, right? So we'll do that also. LoRa config. Okay, so looks good. Yeah, so let's run this. Oh, process not defined. Okay, import dot. So while it is downloading, I'll say about the rest. Okay. So for attention module, I'll show you how to do that. And for task type, for now there are two types, right? We have seen about there is also some other things you can do, sequence classification and all. So seek underscore CLS, you can do image classification also by using LoRA. For now, we have seen about seek to seek LM in some previous video, but here we are doing causal LM. Okay, causal language modeling. Next, we are creating a tokenizer and we are setting our pad token to be our US token, end of sequence token. Okay. Now coming on to the training arguments where we have provided our output directory, which is SFT Santa coder 1 billion, and train batch size is 10, eval batch size is 10, gradient accumulation steps is 2, where after every step, 2 steps only, the optimization will takes place. Okay. Learning rate will be 2e minus 4, which is 0.0002. And for every 10 steps, we'll be logging and we'll be training it for 100 steps alone. So these metrics, whatever we'll calculate, it will be stored in a tensor board. That's why we have report 2 is equal to tensor board. So next we save the model at the 100 steps at each 100 steps, but here there will be only one save because we are setting the max steps is equal to 105. Okay. Next, for LR scheduler type, there are a lot of types. Here we are using cosine. Okay, there is some other types like linear and all. It's there. Next, for warm-up steps, we have one, and then we are using paged Adam W 32-bit optimizer. So these are some special optimizers. Paged optimizers are some special optimizers created for QLoRA. Okay, and we are doing a mixed precision training where we are training in precision 16. That's why we are setting FP16 equal to true. Okay, so then we have a running name. Okay, for this run we have set the name as SFT Santa coder 1b. Okay, so same as our output directory. So once we create the data sets, we are passing it to the SFT trainer where model is passed, train dataset, eval dataset. We have passed our pef config. Okay, packing it to true. I hope you guys know about it. Like nowadays, I think I've explained in one of the videos where we'll be having a lot of sequence length uh, samples, right? What it will do is it will try, let's say we have 512, okay, 512 as our sequence length, 512 tokens, but let's say we are having the first sample as 300 and then the next sample as, let's say, 400. What it will do is it will try to combine 300 plus 212 in one sequence, and then the rest will be taken to the next sequence and it will be followed by it. The other samples will be combined. I hope it makes sense. Okay, so that is what packing equal to true parameters does, and then we are passing our tokenizer and training argument. So once we are ready with our trainer, we are just setting it to train. Okay, we are training it, we are saving the model in this directory Santa coda 1b. So once that is done, we are we are saving the adapter model alone. So guys, when you call the model from SFT trainer, your adapter model will be called and adapter config also will be called. These two will be saved in the SFT Santa coda 1b. Okay. Oh, sorry, telling me to do it. It's content folder. Yeah, here it is. Drive. So here if you see, we are having SFT Santa coder, right? In this, if you see final checkpoint, this was the folder. We are having our adapter config and adapter model. Okay, so that will be available in this output directory. Okay, but we need both the base model as well as our PEFT, which is our LoRa model, right? PEFT module or LoRa module. So what we'll do is, for now we will delete this base model and we'll be calling a model, okay, based on this adapter module. Okay, we'll be calling a model So here if you see, we are calling it as RTOF model for cause LLM from pre-train. Okay, so by this it will create a model, and we'll be merging this model with the original model. Okay, so that is what we are going to do. Okay, so merge and unload, what it will do is, previously you will have, when you print the model, right, you will be seeing separately, like there will be LoRa A, LoRa B, it will be specified. But once you do merge and unload, it will be merged with its original respective layers. Okay, so once that is done, and if you save it again, so it will, if you save it in safe serialization equal to true method, it will be stored as safe tensors. Okay, so when I trained it, here you can see, right, the loss was constantly decreasing. There was this was the only occasion where it got slightly increased, and again it started to decrease. Okay, 3.15, 3.05, 3.00, 2.99. It was constantly decreasing, which shows that with some subsequent training and increased number of samples, still the model performance can be increased. Okay, so that was about SFT training. Okay, so you can execute this. I'll provide all these notebooks in the GitHub link, in the GitHub repository, and I'll provide the link in the description. Okay, so guys, without forgetting, try to save this model. Okay, because it might be needed in the future for you all. But if you think like, okay, I'm not gonna have some storage, then you can also do push to hub. Okay, now coming on to finding the attention module. Okay, so what you can do is print base underscore model. Okay, so if I print it, right, so here you can see we are having attention module here. Okay, so in attention module, which is GPT big code attention, your attention is CATTN. Okay, so that is your attention module. So for that, we are considering this LoRa module. Okay, so you can also do it for cproc, but the reason I didn't do it was the projection layer was also used in MLP. Okay, so if you have seen the previous research explanation, they avoided MLPs, right? So I didn't mention it here. But while doing DPO, I considered C projection as well, because like to have some better performance. Okay, there is no other reason, but still, like in this stage also, in SFT stage also, you can consider using C projection as well. So this is how you need to find your attention module, because for each model it will be different. Okay, so yep, that is about making your SFT model. Now let's jump on to creating the DPO model. So similar imports, but before that we are mounting the drive and then we are copying it here. Okay, so that will be there. Cancel. So similar installation and login. Okay, so similar imports as well. But here for there is a function called DPO data, which we'll call here. Okay, in later, but let's see first how to call the model. So AutoClift model for causal LM, we are using that class to call our model. Okay, in here we'll be using the model which we trained previously, SFT model. Okay, so other than that, we are loading it in 4-bit, which means we are loading it in a quantized manner. Okay, this model will be same as this one. Okay, so the reference model and the original model is the same, and the other. Okay, so yep, that is about the model. And similar setup, like, we'll call the tokenizer and set the pad token to US token. So now to get the train dataset, we'll be calling the function called DPO data, and we'll be passing a parameter called train. Okay, so the dataset which we are using is again the full HH-RLHF, but the train split. Okay, so that is what we are going to use. And what we do here is, here the data set will be slicing it. Okay, like is to 10,000. We'll be just considering the 10,000, and here also, like, we'll be considering only 4,000. Okay. So after that, we'll have this original columns, which is the column names. Okay. Yeah, I was just confused, like, I forgot to comment this actually. These are all not needed. Like, I was just using the same dataset for training and evaluation. But, like, similar to SFT, you can just call the train test split function of dataset, and then you can have a dataset for you guys. Okay. So that can be changed here. Okay. So next, we have prompt and response being connected like this. Okay. So that is there. Then we have chosen, rejected. Okay. So these are all there. So here also, actually, if you see, this won't be needed. Prompt alone will be suffice enough, like I said. So this should be suffice enough. Okay. So yep. Now we have this function called return prompt and responses, right? So we'll be mapping this on our dataset. So here, this won't make any sense. Okay. I'll just remove these. Okay. Always will be loading the whole dataset. But yep, I guess this is good. So once that is done, we'll have our train data as well as val dataset. Okay. So in that, what we are doing is, like, we are just filtering the dataset where we are trying to find the samples where when we combine both prompt and chosen, when we combine it, the length of the token should be less than 26, 256, sorry, not 226, it is 256. We are filtering those datas alone for the trained dataset. Similarly, we are doing the same for the eval dataset. So, but whatever the count it is doesn't matter, because we'll be changing the max steps here. But if you want to train it for longer times, no issues, just remove this parameter and it will work. Okay. Or I'll set it to some 1 million. Again, it will work. Okay. Uh, so training arguments here, I'm not just going to explain the similar parameters which we saw previously. Okay. Train batch size, max steps, logging steps is equal to 10, max steps 505, save step 500, gradient accumulation steps 4, gradient checkpointing is equal to true, which means we'll be storing the gradients, okay, at the checkpoints. So we'll have learning rate, evaluation strategy, where we'll be evaluating based on steps, 100 steps, okay. So output directory is given, report to. I think all of these are similar to what we used in SFT. But here, if you see, the only changes I have added C projection. Okay, other than that, nothing is different. Still, you can use the same one. Next, in DPO trainer, this is where slightly things are different, but not as different. Okay, so we'll be passing the model, which is this one. This is the model which will be optimized. Okay, DPO optimization will be happening on this model, and the reference model is also the same, but this won't be optimized. That's why here use case is equal to false, but here it is not given like that. Okay, so we are providing the reference, which is your optimal. If we see in the research paper, right, they would have given it as optimal policy and reference policy. This will be your optimal policy, and this will be your reference policy. Okay, we are providing a training argument, and we saw, right, beta parameter was there. So beta is equal to 0.1. We are having train and eval dataset, followed by tokenizer. We are having a pref config, which are all something which we have seen till now. Max prompt length. This is another thing, like, we'll be having the prompt length will be around 128. We are just saying, like, at 128 tokens, your prompt will be almost over. Okay, so that's how we are just letting it know. Okay, but it might not be like that. So we are just saying, like, half will be the max range for the prompt. So followed by that we are having the max length, okay, which will be equal to 256. Now we'll be training the model, we'll be saving it. So similarly we'll be storing the adapter model, okay, but don't do these two steps. These two steps resulted in error for me. This won't work here, okay. So but before going into that, let's see, like here, the reward source is good, right? Like it was decreasing. We seen the explanation about this in the previous video. So if you haven't seen the explanation of DPO, check it out. Okay. So once till now, till storing the adapter modules is done, then execute this cell. Okay. So in this directory, which will be just a minute, I guess. Auto model for, yeah, yeah, correct, correct. So here what we will be needing is our SFT model, right, where we merged the LoRa modules, which was the base module here, right? That is the model which we will be needing. So first the model will be set as that model, like SFT model. And what we'll be doing is we'll be combining that model by using this DPO Santa coder. Okay, so that's why we are providing this path, the adapter models, which has been saved in DPO Santa coder 1B and slash final checkpoint, that folder. Okay, from that we'll be combining the model, from which we'll be getting the final DPO model. So that is what you will obtain from here. Okay, so that you are storing it and then you can push to hub like this. Okay, so I'll also show you the size actually didn't matter. As if you see, I actually have made a lot of uploads. Now let me check it actually. DPO Santa code. Here it is. So here you can see, right? Like we are having the same size model, 2.25 gigs. The size didn't even change. Okay. So that is what I'm trying to say. Like it is very less in size, but the LoRa gives great performance. Okay. So that is about making a DPO trainer. Okay. And then finally you can infer it as the conventional text generation, as a conventional text generation method. Like, you need not do any auto model for causal LM or anything like, sorry, not your auto model, for auto PEF model or combining the PEF model, that won't be needed. Once you do this model equal to model.merge.unload, what will happen is the LoRa modules will be combined with your original model. Okay, so once that is done, you won't be needed to explicitly make a pipeline out of it. You can also simply do some testing with this pipeline function, where we have set that the max length should be 256. We are considering top P to be 0.9, and then we are setting CUDA device and no repeat engram size is equal to 3. And once we gave this kind of an input, we got some results, right? We have saw about this in this video first itself. So yeah, and the trainer we used was this one. Okay, so DPO trainer, and actually this is a very very long file. Okay, you can see, right, it is 454 files. So if you want me to make a detailed explanation on this also, just let me know. Okay, like I said, I'll make a playlist on this TRL library very soon. So yeah, guys, I hope you all understood about how to implement TPO on your own model. Okay, so here where and all you can make changes is that you can change the model checkpoint. Okay, and play with some hyperparameters of training arguments or even your LoRa parameters. Okay, those are some hyperparameters you can play with, and maybe you can also play with the dataset, but the dataset should be of this specified format. Okay, so let me not do that. Full-hh-rlhf. Okay, so you should have a prompt. You should have a chosen response as well as a rejected response. That would be needed. Okay, which is here our preferred response and dispreferred. That was needed, right? Like for our DPO, we saw that, right? So that is the only prerequisite for applying it on a data set. Maybe if you create a custom dataset for a custom use case, let me know. So I'm very interested to look on how it will work. Okay. So yep. So that is DPO implementation for you guys. So if you haven't liked the video, please consider liking the video. Okay. So if you haven't subscribed, do subscribe because only 35% of the viewers are watching my video are subscribed. So 65% has not. So please consider subscribing and more importantly, share it with your friends and colleagues who will be interested in similar content. So that is for this weekend, guys, where we saw DPO paper explanation in detail, and followed by that, we implemented it on a model called Santa Coder. So, yep, just test it with your side and let me know if you face any error. Just let me know in the comment section. I'll try to help you out. Okay, so I'll see you all in the next video. Until then, cheers.